explain what's going on here. I'm trying to think of another way I can get this to you right now. Nothing's coming to mind.
That's all right. I'll listen and I will figure it out.
Okay. So back to what a prism is. So a prism is a 3D figure where there's a top and a bottom. Those are called the bases. They're parallel and congruent. So the simplest possible one would be just like a regular cardboard box.
Okay.
And then think back, like when I first discovered the word prism, it was in elementary school science class, and there was this really cool glass shape that was triangular but long, and it turned light into a rainbow. You guys remember those? Yep. Right. And so that would be a prism with a triangular base. Okay. A doorstop is a prism with a triangular base, different than the glass kind that reflects light. And so there's all different shapes and sizes of prisms. But the cool thing about a prism in terms of its volume, if you know the area of its base and you multiply by its height, then you have the volume. And if we just think about a rectangular box and extend that idea, that's pretty much what's going on. So with a rectangular box, we have a base and a height and a length, or I should say length and a width and a height. And if you take the length times the width, that gives the area of the base. So one common formula for a box is that the volume is equal to the length times the width times the height. But if we break off that length times width and say, hey, that's just the area of the base, then we can also view volume as the area of a base times the height perpendicular to that. And that's important. The base and height have to be perpendicular for this to work. So Debbie, do you have your print book?
I do, yes.
Okay, so if you open up your print book and go to section 14.5, let's see, where's my book? Let me grab my book to double check that, but I'm pretty sure it's chapter 14, section 5.
So what is the rule that bases?
For the length, the base times the height one, or for
So I'll try to relate everything I say to stuff in the book. That way you'll have visual images to go with it. Now. Okay, so 14, yes. 14.5, yes. So consider page 896.
Okay.
And there they show a section called Volumes of Pyramids and Cones. And they've got a capital B pointing to the top of that box there.
Yes.
And that's what I'm referring to. So that's congruent to the base parallel to it at the bottom.
Okay.
So if you just take that base and multiply by the height, imagine filling it with water. The top of the water is the cross section of that thing. And as it fills up, it's making volume. Right? Like pouring water into a box.
Okay.
And so that's one way to think about pyramids. And it turns out from our coffee demonstration, and then on page 897, they've got that same thing we were working on, where we have a cone that fits inside of a cylinder. And what you'll see is that the cone only holds a third of what the cylinder does, or vice versa. The cone can fill the cylinder exactly 3 times if everything is built right and everything is measured right. which is just amazing. And the connection between the 1/2 base times height for triangles and rectangles and the 1/3 base times height for prisms and pyramids is moving from 2 dimensions to 3 dimensions. That's the key.
Okay. So that's what like is basically is that how they get like the 3 dimensions because you have to 3 of it?
Yeah.
Okay. I was
Yeah.
wondering.
In 2 dimensions, there's 2 of the triangles. In 3 dimensions, there's 3 of the pyramids that live inside. And you can see it more with the cube cut into congruent pyramids. It's harder to visualize with the cone. Unless you have a cone you can fill with water or rice and really measure it to see it happen. But it's pretty remarkable that it works out that way.
Could you explain the, I'm kind of confused about the length times base times height, but only if the area of the base times the height is parallel.
So the definition of a prism
Okay.
is what that was. So
Okay.
yeah, so something is a prism if it has a pair of congruent bases that are parallel. And is there a similar picture in the book? So what we're describing here would be back in 14.3, the book, Debbie.
Okay.
And this would be page 867 in the book.
Okay.
And the figures at the top and the bottom mostly. So for example, a can, which is a cylinder, that has a circular top and a circular bottom. The circle at the top is the same shape and size as the circle at the bottom, and they're parallel.
Right.
So there's congruent parallel bases. Because you can
Okay.
flip the can upside down, it doesn't matter. It's still the same can, right?
Right, yeah.
Yeah. And then consider like the kind of prism that you would shine light through and the light would turn into rainbows. So that would be like this guy right here.
Uh-huh.
It's got a triangular base and a triangular top that are congruent and parallel.
Okay.
And then perpendicular to those bases are what are called the lateral faces.
Okay.
And the lateral faces can be congruent. They don't necessarily have to be, but they have to be perpendicular to the base to be a prism.
Okay, and then, so I guess I'm confused by what that has to do with, because you were talking about how to find the volume, and
Yes.
it's length times width.
Yeah. So to talk about volume, I oversimplified a little bit and talked about a box. Okay. And in a box, the base is the length times the width.
Right.
Right? And if I take that base and multiply it by the height, I have the volume. And it turns out that generalizes to all...
Base times height.
Area of base times height generalizes to all, not the length times width part, but the area of the base part.
Okay.
So if we look back at these other possible types of prisms, which are also listed on page 867 in the book, if I take, for example, a hexagonal prism, which is figure 1450C in the book, or this blue one on my screen here, if I find the area of that hexagonal base and I multiply by the height, bam, I've got the volume of this thing.
Okay, so that's what you were saying.
That's what I'm
okay,
saying,
I was
yeah.
confused by
Yeah.
it.
So for any prism, if you can find the area of the base, for a box, it's length times width. For a hexagonal base, it's more complicated.
Okay.
Yeah. For a triangular base, it's a little more complicated. For a pentagonal prism, it's more complicated. But once I find the area of its base and I multiply by its height, the volume is done.
Okay.
Yeah. So that was the point. In general, for prisms, if you can find the area of the base, then you multiply by the height, you're guaranteed to have the volume. But it gets better than that. Believe it or not. Greg is stunned that it gets better than that. So to kind of give an analogy about how it gets better than that, I'm going to go back to talking about the idea of a rectangle. If I put a diagonal in a rectangle, I make 2 triangles. And those 2 triangles are congruent. Well, it turns out I can do the same thing with any parallelogram. So I build myself a parallelogram. So draw yourself a parallelogram, Debbie.
Okay.
And then grab one of the diagonals for that parallelogram, either one, and draw it in. That diagonal cuts the parallelogram into two congruent triangles. What is the area of the parallelogram? Well, if I pick one of the sides to be the base and then extend it, the height is going to be perpendicular to that up to the top. And the bottom line, just like a rectangle, area of a parallelogram is just its base times its perpendicular height. And the same thing is true for those triangles. Those triangles are half of that parallelogram. Okay. So now, let's see. So in the book, Debbie, I would direct your attention to page 867 still.
Okay.
At the bottom, they show a hexagonal oblique prism.
Okay.
And then above that, figure D is called an oblique cylinder. And oblique means its base is not at a right angle to its sides. That's what oblique means in 3 dimensions. So let me get some pictures of that for the in-class audience here. So oblique prism. It's lovely images that pop up. Here we go. And so just like a rectangle is similar in terms of its area to a parallelogram, the same thing works for an oblique prism. An oblique prism just means the lateral faces aren't perpendicular. But what we really do have to have happen, the bases still have to be parallel. Otherwise, things go to heck. So for example, in one of the images I have here, I have a right rectangular prism next to an oblique rectangular prism. And the bottom line is, as long as the bases are parallel, and I know the area of one of the bases, I just multiply by the perpendicular height, and that gives me
I have to go.
Okay, we're just about done here.
Okay.
I'll email you some information about art project.
Okay. Thank you. Bye.
Yeah, so just like we can generalize the area of a rectangle into the area of a parallelogram, we can generalize the area of a right prism to an oblique prism. And as long as we know the height perpendicular to the base plane, and we know the area of the base, we know the volume. It doesn't matter that it's slanted, provided that the top and the bottom are parallel. And one way to think about it is imagine, anybody ever buy those big bundles of paper for your printer, right? That's a rectangular box. But as soon as you unwrap it, doesn't it easily go askew? Okay? So you can push it in such a way that that rectangular right prism turns into an oblique right prism. But doesn't it still have the same amount of paper in there? And each of those pieces of paper is a piece of volume. So it still has the same volume even if you tweak it. Does that make sense? Yeah. Yeah. So it's pretty remarkable about the way this stuff just kind of works out.
So when we come across problems like this, will it give us the height or give us the slant height, or what will it give us?
Yeah, so that's a good question. In order to calculate volume, we would have to be able to somehow figure out the area of the base and somehow find the perpendicular height.
Okay.
That's because those are the important measurements. And so let's take a look at the stuff I assigned for homework, and then we'll talk about art projects. And we only have 2 more days after today. I can't believe it. So we got to get some art going. Yeah. Let's see. Where's homework live? Homework lives here. Do homework. Okay, so the stuff I added was 14.3, 4, and 5. 14.3 is mostly homework about classification. Is it a prism? Is it a pyramid? And then some little cute math things in there. So some of these are kind of mathy puzzles, and you're gonna have to think hard about them. So let's just pick one and see what happens. Like number 11 might be cute. Oh yeah, so this is one of the 3D where we have to take this net. So this, okay, so in the book, sorry Debbie, I forgot you were in a different world.
That's okay.
So this is section 14.3 in the homework, and the one I'm considering now is like number 9, in section B of the homework, 9B. So if we have a net of the figure, so all a net is the faces of the 3D object flattened out. And you could fold them and tape them to make the real object. And so if we were to take that net listed in the book, or to take that net in the screen here and fold it into its 3D object, which in this case would be a cube, it's got 1, 2, 3, 4, 5, 6 faces that are all squares. Which of the 3D images they show would be the right one? So we're trying to do three-dimensional visualization. And there's a lot of studies that show that kids that play with blocks are really good at this as adults. And so like on this one here on the screen, I think D looks like the right one too. And in the book, I can't. The black triangles are going to be in opposite faces compared to the triangles that are nested in each other. So it's not 1, it's not 2, it's not 3, it's got to be the 4th one in 9B in the book. Okay. So let's see. Okay, Greg says it's similar to the one in there, and then let's see. Check answer. Oh, it's the wrong one. Okay, so this gets folded over and is going to be perpendicular, and that one's perpendicular too.
Yeah, but it turns when it folds in, one turns into parallel. That one's parallel to that line.
Oh, these two are on opposite sides.
So
it's got to be B. Yeah. Oh, there it is. Okay, so let me double check 9 in the book. So 9. Yeah, 9B in the book. I am 90% sure the 4th one is the right one to match that up with. Yeah, so some of this is about spatial visualization. Others are about puzzles. So let's see, what is this one? This would be like, which one in the book? 14.3.3. So this is a mathematical connections number 3 is the next one we're looking at, page 877. And the question is, are both of these images of a quadrilateral pyramid? So a pyramid with a square base. And so my interpretation is A is looking at it from above, and B with the dotted lines would be looking at it from underneath. So I would say, yeah, these are the same figure. So I can't read either. Yeah, so they offer us options on how to answer this in the book. No, the drawing is not a quadrilateral pyramid. Yes, you would be standing directly below the pyramid. So what's the question? Can picture A be a drawing of the quadrilateral pyramid? If yes, where would you be standing in this case? Okay, so for figure A, we'd be standing directly above the pyramid. And then for B, we'd be standing directly below the pyramid. Oh, what? Did I read that wrong? You would be standing directly. Oh, I hit above when I meant below. There we go. There we go. Okay, apparently I can't read. So I assigned some problems from assessment A in the book, a couple problems from assessment B to get more practice. And part of it's what's the difference between a pyramid or a prism. Part of it is spatial visualization. And then there's a couple of like way back from Math 211 problem solving things that pop up in here. None of them are too bad. Not like the staircase problem. All right. You remember the staircase problem from Math 211? That's probably good that you don't remember it. All right. So I'm going to go back. Yeah, every year I think maybe I shouldn't assign that problem anymore. It's kind of painful. Section 14.4 is all about, I didn't assign too many there. That's about surface area. And I focus mainly on volume today, but surface area is kind of interesting. With most prisms or pyramids, it's just a bunch of rectangles and triangles mainly, and you find the area of each stage and add them up. There's nothing all that special about them. The coolest one, however, is the cone, because the cone, where did that go?
It's going to be kind of like a rectangle.
Yeah, the cool thing about a cone is, the cylinder in the cone, the cylinder is just a rectangular piece of paper rolled up and connected, right? The label, all a cylinder is like a label rolled up.
So if you think,
So if we wanted to analyze so here the longer edge would be the shorter edge would be the height in the one we're drawing from the book, and the longer one turns into the circumference. So if you wanted to get surface area of a cylinder, and you ignore the top and bottom, you're just looking at the side, it's just a rectangle. So you have length times width. Your width is the height of the cylinder, and your length is the circumference of the can. Right? Imagine opening that back up again, which is kind of cool. So you get a relatively simple formula as long as you know circumference. It's just circumference times height, which is kind of neat. So there's not really much exciting except for the can, I think is the most exciting part of surface area. Otherwise, surface area of 3D objects just gives you more practice of area of 2D objects. Because you have triangles, you have rectangles, the exciting pentagon or hexagon that pops in to make life more interesting. And then the other bit of homework I assigned was in section 14.5, and 14.5 is about volume. That was the stuff we were just playing with. And most of those problems are pretty straightforward. And I set a due date of the 3rd of June for these, which is the end of next week. So we should have plenty of time to get these done. And so some of the problems I assigned, Debbie, if you compare to the book for 14.5, would be like number 4 in assessment 14.5a.
Number 4?
Yeah, number 4. There is one formula I have neglected to go over so far. So we have prisms are pretty straightforward. Pyramid is just 1/3 of a prism, so 1/3 base times height, where the base is an area. Sphere is very different, and it's kind of a wild one. And so that one, I'm just going to have to give you. The sphere is 4/3 times pi times the radius cubed. And I don't have anything cute in terms of remembering that or why it is without calculus. And my apologies, I don't want to go to calculus right now.
times pi times what?
4/3 times pi times the radius cubed. the book gives a cute way of looking at it, which is all right. But think about the area of a circle. That's pi r squared. If we go to 3 dimensions, something has to get cubed. You need 3 dimensions to have 3 dimensions. So radius, radius, radius is the r cubed. It's a circle, so pi's got to be in there somewhere. And then the 4/3 is just this magical constant that pops up in there. And I don't have an intuitive way to explain that. So that's one of the weird formulas. Otherwise, when we were doing the metric Olympics, we talked about the relationship between liters and meters or centimeters. And so just a couple of notes on that. There are 1,000 liters in a cubic meter. That's a good piece of information to know. There's 1,000 liters in a cubic meter. Similarly, there's 1,000 cubic centimeters in a liter. 1,000 cubic centimeters in a liter. And I probably should be writing this down somewhere. And then if you kind of take those 2 pieces of information and think about it a little more, so again, we've got 1,000 liters in 1 meter cubed. We've got 1,000 cubic centimeters in 1 liter. And anybody remember what milli means in the metric system? Milliliter versus liter? It's a thousandth. So there are 1,000 milliliters in 1 liter. And so 1 milliliter is the same as 1 cubic centimeter. Yeah, 1 cubic centimeter. So there's a kind of cool link between liquid volume and like rectangular volume. A milliliter is a cubic centimeter. So you might have heard, like with doctors and hospitals, when they talk about adding a certain drug to something, they might talk about cc's, which is the same thing as a milliliter. cc stands for cubic centimeter. So sometimes this is expressed as 1 cc. cc stands for cubic centimeter. So cc and a milliliter are the same measurement.
And it's gone.
Should be coming in just a minute.
It's gone.
She just ran to the store.
It's not open.
Okay, I'll be up there in just a
It
minute.
was black.
I'll be up there in just a minute.
Okay, so those are the basics of everything there. We'll need to do some troubleshooting on homework soon, and we also need to start thinking about an art project, and that's how we're going to finish off the term. We have some homework to tidy up, and then we have some art to do. So on Wednesday, I'm going to bring in some art supplies. So I'm going to have glue stick and glue guns and soldering irons and all kinds of little pieces of metal and wire and what else was I bringing? I'll have all different kinds of paper to play with. This Wednesday? Yeah. And next Wednesday. We may be able to get access to the 3D printer, although I don't know anything about using it or setting it up or anything like that. But maybe I can get our 3D printing, my 3D printing friends to come and show us some cool stuff. And so stuff to think about for an art project, we have lots of 3D stuff we did. If you look in the book in section 14.3, they talk about the Platonic solids, which is something I was going to talk about next class. So Platonic solids, and this would be on page 870 in the book. Platonic solids are quite fascinating. So you know, in 2 dimensions, we have lots of regular figures, like we have regular triangle, regular quadrilateral, regular pentagon, regular hexagon, and so on. In 3 dimensions, there are only 5 regular figures. Whereas in 2 dimensions, you pick how many sides you want, there's a regular figure for it. Right? Regular 12-sided figure, regular 10-sided figure. In 3 dimensions, it turns out, and you can prove this geometrically, there are only 6 of these guys, or sorry, 1, 2, 3, 4, 5 of these guys. Anything else is just not quite regular. So what does something have to be regular? Well, in 2 dimensions, all of the angles have to be the same, and all of the faces or edges have to be the same. In 3 dimensions, we have angles in multiple directions. We have edges and faces. So that means all of the edges would have to be the same length. All of the faces would have to be exactly the same shape and size. And all of the angles in between the edges have to be exactly the same everywhere. And these 5 figures are the only ones that meet those conditions. There's a ton, though, of semi-regular ones. Like, there's a whole classification called the Archimedean solids, which are just mind-blowing to me. Archimedean solids. And they are not in the book, unfortunately. Sort of. On 872, the next page, they show a truncated icosahedron, which probably would show up here too. Let's see. The truncated icosahedron is, really? Oh, there it is, right there. Can I blow that up anymore? Oh, whoa, that's going the wrong way. Let's view this in a new window. Open image in new tab. Okay, here we go. And then blow them up. So this is the truncated icosahedron. What does that look like? What's that?
Disco ball.
A disco ball. Okay, what else? So this is also on page 872, the figure on the left at the top.
872?
It is a soccer ball. What's that?
872?
872 in the book, yes. Yep.
Okay.
The truncated icosahedron. That's a soccer ball. People know that a soccer ball is also a truncated icosahedron. Not very many. And then there's tons of other figures. And so I've made some of these with like toothpicks and glue or soldering iron and little pieces of wire or pieces of paper. It gets kind of tedious for some of them. If you look out on the internet, there's paper nets of all of these. So you could try to print them on cardstock and cut them and tape them together. But given how exciting today was, you're probably not going to want to do that. Other kind of cool things that we could do for artsy geometry. We skipped over chapters 12 and 13 in the book, and there's some really cool stuff in 12 and 13, if I can find the book again. Did I ever bring it up? I don't think so. So chapter 12 is about congruence with similarity in construction, and 13 was about congruent similarity with transformations. And in there, they get to an idea called tessellations. And where are tessellations? I thought they were, oh no, tessellations are in 13. Yeah, tessellations of the plane. And so remember our pattern blocks we played with before? You can use the pattern blocks to tile an area. It turns out you can do regular and irregular patterns to do so. There's a lot of cool stuff there. Like Greg could use the pattern blocks to make a geometric version of the death moth. Is that what it's called? You could either stick in the realm of stuff we've played with and do something artsy with like the Pythagorean theorem or circles. We could do something artsy with 3D figures. But the goal is to make something geometric and pretty. So it has some cool property to it, and it's also attractive. And attractive is a measure of one's own preference. So, you know, you guys can decide what that means. So I'm leaning toward doing something with the irregular solids, so kind of like the Platonic ones, but more in the Archimedean, like the truncated icosahedron, aka soccer ball. I've seen lots of cool videos where people do like origami versions of these things, which I've never been. I'm a pretty good paper folder, but I lose patience with origami. But I love playing with glue guns and soldering irons. And then we could like wrap it in yarn or something. So think about that. I'm going to send out, like Kelly missed this discussion, so I'm going to send out a whole bunch of suggestions with pictures and websites to take a peek at. So the next two classes are to tidy up any homework we have, any activities, and to play with building something. Debbie, if you need anything in the way of gear to build some idea you have, let me know.
Okay.
And I'll see what I can get you.
All right.
That's it for now. Looks like you got your hands full there.
A little bit, yes.
Okay. And then I'll look up your problem with Windows 10 and see if I can figure something out. And then I'll send you a link to the YouTube channel, and you should be able to view stuff there, which is slightly different than Hangouts.
Okay.
All right.
And do you know what day our
Oh, what day our final is? Good question. Let me check the schedule. Blue CC. Calendar. Final exams. You think it's Monday?
It has been for the last two,
Oh, okay. So it's probably the same then.
or maybe was it Wednesday?
So when do we
Was it
meet?
last time?
We meet at 3 o'clock. It says it's Wednesday.
Oh, yeah, Wednesday.
And it says Wednesday at 2, but that's a typo. It's supposed to be at 3.
and that's the 8th?
That would be 8 sounds. Is that right?
Last week.
All right, sure. Yeah.
Okay.
So I'll put up a sample final, and it'll be part take home, which I'll have the take home ready for you next week.
Okay, sounds good.
Okay. All right. Hopefully we'll figure out these technical problems. We only have 2 more classes, so I guess it's not that bad.
Right.
All right. Good luck with your handful there.
Thank you.
Catch you later.
Yep, have a good one.
You too.